All right, today is the first of two lessons that when you look at them at first glance, they can seem kind of overwhelming because you see this word theorems in here. We're going to have some theorems about roots of polynomial equations. And so it's kind of intimidating at first because there are a lot of words. However, my hope is that as we look at this, we say, oh, I can kind of see like what this theorem is saying. It makes sense. Or start to understand the reasoning behind why we're doing this. First of all, one of the reasons that we're using these theorems is because there are going to be times when you're given, I'm just going to skip ahead a little bit. You're given a polynomial like this and told to solve it for x. And if I haven't given you anything, we haven't learned how to do that. So we're going to look at these theorems and figure out how can we solve for x, basically. So the scary, quote-unquote, scary version of this theorem is this, and I'm not going to read the whole thing to you, but notice that we have a polynomial in standard form. The exponents are going in descending order. It does say that the coefficients have to be integers, so it can't be like 3.5. It has to be -2, +7, etc. Then we've got these values of p and q, and so we really need to know what these values represent. P represents all the factors of a sub 0, or in other words, the constant that's at the end of our polynomial. And q is a factor of a sub n. So here's kind of the, in other words, version. We find all the factors of the constant p and all the factors of the leading coefficient, q, and then the possible rational roots are p over q. And so what we're going to do is list factors for first term and last term, and then do the factors of the last term over the first term. If you're not really tracking with me so far, that's okay. We're going to put it into practice here. So the first thing we're going to do is find our values of p and our values of q. P is the number that's at the end of our polynomial, and we're ignoring the sign of it. So I'm just going to put 8. Q is the number that's at the beginning with the largest exponent. In this case, the number in front of our highest degree is 1. The coefficient of x cubed is just a 1 because nothing's written. So now we're going to find the factors. So this is kind of taking you back to elementary, middle school math. But factors of 8. I need all the numbers that I can divide 8 by and not have a remainder. So what are all of the factors of 8? I'd have 1, 2, 4, and 8. And all the factors of 1, just 1. That's the only number that we can divide 1 by. So now what I'm going to do is I'm going to do this p over q thing they were talking about, and I'm going to take each of these factors and put it over our q value. In this case, we only have one q value. So I have to account for both the positive and the negative because I could have positive 1 over 1 or I could have negative 1 over 1. And that negative, it doesn't matter which one it's with. Don't worry too much about it. Just know that we do need to always put plus or minus. So I'm going to put p over q. So I'm going to do 1 over 1. Now I'm going to do 2 over 1. 4 over 1, and 8 over 1. And now I have 1, 2, 3, 4, 5, 6, 7, 8 possibilities of possible roots for this problem. Oh, this was supposed to be a plus. I thought I changed that. Sorry. So what we need to do now is actually test them. And we are going to use any of these 8 values in synthetic division to see which one or ones work in order to solve the rest. So we're going to say determine which ones of these are actually rational roots for the polynomial. So I'm just going to pick a random number from here. I could do 1, -1, +2, -2, etc. I'm going to pick 2 to start with. All right, so I've got 1, -4, 2, -8. So I'm going to bring down my 1, and then I get 2, -2, -4, -2, -4. That does not give me 0. I need a remainder of 0. So this is where the unfortunate part of this method comes in, is it's just, there's no other way to do it than to just guess and check. So we're going to try -2 now. And when I do that, I get 1, -2, -6, 12. This is going to be too big. That's not going to give me the number I need. Let me try 4. I'm just picking these randomly. I'm not sure what's going to work and what's not. Some people start from 1 and work their way up. Some people work their way down. I clearly like to start in the middle and just mix things up. All right, so I get 4, 0, 0, 2, and then 8. Hey, there we go. That's 0. So this means that 4 is a rational root. So that's one of my answers, x equals 4. Now I need to find the rest of the roots. Now these are not necessarily going to be rational roots, but if I write this as a quadratic, what would this look like when I write my answer out with the variables involved? I would do 1 less than the starting coefficient, or starting exponent, excuse me, so I'd have 1x squared. I could put plus 0x, but I don't have to, and then plus 2. And I'm going to set this equal to 0 because I'm going to solve it. And to solve it, I'm going to subtract 2 to both sides, and that gives me x squared equals -2. I've been on one color for a long time. To solve this, I'm going to take the square root of both sides, and that's going to give me x equals plus or minus I radical 2. So then I also had my answer of 4. And because I started with a degree of 3, I should have 3 answers. Here I have 1, 2, 3 answers. Plus or minus, it gives me 1 of each, and then 4. All right. I'm actually going to skip over this one for now. We'll practice a little bit more later, but I want to make sure that we get to these other theorems. So these are the theorems that I think make a little bit more sense. They're more intuitive maybe. So what this says is that if we have an irrational root or a complex number where it's like a plus a radical or a plus a number with I, we also have the conjugate, which just means that this middle sign, only the middle sign, is going to change. So notice, like, if I have a plus radical b, I also have a minus radical b. So if I have these as my roots, if I have 2 minus radical 7, I'm also going to have 2 plus radical 7. If I have square root of 5, what's my other root based on that going to be? Negative radical 5. And that's it. That's using the irrational root theorem. All right, so now we are going to find a third degree polynomial that has rational coefficients with roots -1 and 2 minus I. Now it's a third degree polynomial, so that means I need 3 terms. Thinking back to lesson 6.2, this is where we said, okay, I've got -1, so I'm going to, when I write the factor for that, it's going to be x plus 1. Now, this one is a little weird because it is 2 minus I. Here's how we're going to write it. We're always going to write minus, because technically, if you think about it, this is x minus -1, but I'm going to write x minus 2 minus I, and so I have my value here. But since it's a third degree polynomial, I need 3 factors. What is my other factor going to be? I also need 2 plus I. If I have 2 minus I also have 2 plus I. So I'm going to write this as x minus 2 plus I. Now, this is not as bad as it looks, I promise. What we're going to do is think about distributing this negative in both cases, and I'm going to ignore the x plus 1 for now. X minus 2 plus I and x minus 2 minus I. And here's what's going to be really great is that when we, for lack of a better word, FOIL these together, our i's are going to disappear. The letter I is going to disappear. So I'm going to distribute this. X times x gives me x squared. Then I have x times -2 and x times -I. All right, now moving on to negative 2. Negative 2 times x is negative 2x. Then I get positive 4, positive 2i. Then I have ix, negative 2i, and negative I squared. Wow, that's a lot of terms. But we knew that it should have 9 terms because we have 1, 2, 3, and 1, 2, 3. 3 times 3 is 9. Got them all. All right, let's do some simplifying. I know that I squared is equal to negative 1. Let me look at what my like terms are. I've got 1x squared, no others. Now I'm going to look for x's that have a number with it. So I've got this one and this one. I think that's it. I've got some x's with i's. I have i's with numbers. And then I have some constants. All right. So x squared was the only one of its kind. So I'm just going to bring that down. So I've taken care of that. Negative 2x minus 2x would give me negative 4x. All right, took care of those. Negative ix plus ix, those are actually going to cancel out because it's negative 1ix plus 1ix. So those just cancel each other. I don't need to write it. I've got 4 minus negative 1. 2 negatives make a positive, so this is going to be plus 5. And then, so I took care of that, and then I've got 2i minus 2i, and those are going to cancel out. And my promise was fulfilled. There are no more i's in our answer. But we're not done. I've got to bring this x plus 1 down. But hopefully this feels a little bit easier because now there's no I involved at least. We can just multiply. So I'm going to get x cubed minus 4x squared plus 5x. That's distributing the x to everything over here. And then plus x squared minus 4x plus 5. All right, let's combine some like terms. I've got x cubed minus 3x squared. I was combining those. 5x minus 4x would give me plus x. Got those taken care of. And then plus 5 at the end. So this would be my final answer. And a real easy way to check it is to say this is a third degree polynomial. My highest degree is 3. So therefore I did something right. All right, let's look at one more like this. Find a fourth degree polynomial with rational coefficients that has roots I and 2i. I only have 2 roots written for me here. What are my other 2 roots going to be? I'm going to have negative I and negative 2i. And so this one's even easier than the previous one because it's not 2 minus I. It's just there's nothing being added or subtracted to them. So let's write out our factors. Go ahead and write this out in factored form using what we did here as an example. All right, so we're going to have x minus I and x plus I. X minus 2i, x plus 2i. And now I would recommend foiling the first 2 and the second 2 together first. So foil the first 2 together, see what you get. Then foil the second 2 together, or the last 2 together and see what you get. All right. So this is what you should have gotten, and I showed my work of when I did FOIL of like getting the first, outer, inner, last, first, outer, inner, last. And when we combine these, the i's cancel out, and then I squared is equal to negative 1. So I could think of this as that, and then negative and negative make a positive. So same idea here. The negative 1 was here, and that together made a positive 4. So then I need to FOIL these together, and when I FOIL those together, what do I get? So this is what you should have gotten when you did FOIL. First, outer, inner, last. Combining like terms gives us this. So I know that the imaginary numbers can be kind of intimidating, but I hope that you're kind of starting to see that even though you had a lot of words here, it's really not too intimidating. It's not too bad. We're going to continue to practice with this. So as always, if you're needing some clarification about something, or one of these things is just not really making sense, please let me know, and I'd be happy to help you in whatever way I can.